Hello everyone, my name is Cece Ahmad. Today I will present our research with title The Development and Implementation of Simulation Software for Data Testing in Electrologix Interlocking. Let us begin with the background and motivation behind this research. Railway interlocking systems represent the most vital, safety-critical backbone of modern railway signaling. A computer-based interlocking or CBI constantly manages track occupancy, switch point positions, and route clearance requests from train control systems, or we call it TCS, before any signal can safely clear. However, traditional verification and validation of interlocking application logic faces severe bottlenecks. Conventionally, testing relies on manual checking of application data alongside physical hardware setups, including object controllers, field input or output modules, and dedicated train control workstations. Manual checking is inherently prone to human error. Furthermore, physical hardware is scarce, expensive, and often unavailable during early development phases. To overcome these critical barriers, our primary objective is to test Electrologix interlocking application data without physical equipment, thereby accelerating project deployment and significantly lowering setup costs. To achieve this, our research establishes three core objectives. Hardware independence, emulating all external trackside objects and train control systems purely inside a virtualized software framework. So minimum or no hardware required for simulation. Automated extraction, replacing tedious manual data transcription with an automated pipeline that passes raw interface configuration files into structured, object-oriented models. This can manual error and overall project timeline. Visual verification, providing an interactive SCADA-based supervisory interface where signaling testers can simulate trains, operate controls, and verify interlocking tables in real time. Our research delivers three key contributions to railway signaling software engineering. First, an ETL data parser. We designed a reusable extract, transform, load pipeline that automatically extracts signaling variables from raw Electrologix configuration files such as .cfg and .dev formats. Second, hierarchical object models. Extracted variables are converted into reusable class-based models representing signals, track sections, points, and routes, accurately enforcing their real-world logic constraints. Third, an integrated SCADA platform. We implemented a unified HMI using PCView SCADA coupled with multi-SIM middleware. This platform supports complete bidirectional data exchange, enabling full factory acceptance testing and user acceptance testing workflows. Our research methodology combines the classic software engineering P-model lifecycle with railway signaling engineering principles. As illustrated on this slide, the research was executed across four main stages. Requirements gathering. We analyzed raw Electrologix interface files and signaling operational standards based on the Victoria, Australia Railway context. System design. We designed the ETL data extraction architecture and developed a modular SCADA symbol prototype library using iterative expert evaluations. Software implementation. We built the PCView supervisory interface, integrated multi-SIM communication drivers, and constructed the class-based data models. Verification and validation. We applied a strict three-layer V&V strategy, starting with automated extraction checks, followed by expert model reviews, and concluding with factory and user acceptance testing. Here, we see the system platform architecture. The simulation environment runs on a standard PC simulator and mirrors complete railway signaling infrastructure. The architecture is divided into two primary operational panels. The TC simulator signalman window, represented at the top, this allows operators to set routes, clear signals, and issue emergency commands. The trackside simulator, displayed at the bottom, this emulates track occupancy, point detections, and field hardware states like Excel counters and smart I/O modules. Communication gateway of these simulators to Electrologix is multi-SIM. Multi-SIM replicates industrial communication protocols, specifically Modbus TCP/IP and safety-critical FSFP2. This ensures seamless bidirectional and synchronized data flow across redundant network channels, exactly as if connected to physical trackside hardware. To empower signaling testers during commissioning and debugging, we developed two specialized real-time diagnostic tools. First is the Wearable Explorer. This module displays live interlocking logic bit transitions in an organized hierarchical tree structure. Engineers can inspect individual subsystem states and troubleshoot data mappings at runtime without needing third-party debugging hardware. Second is Wearable Logger. This provides event-driven historical logging of every single binary state change. It captures rising and falling edges with microsecond-level timestamps, event types, and exact variable tags. This provides full traceability and an audit trail for regression testing and safety compliance. We validated our platform across multiple structured testing phases as summarized in this table. During the data extraction phase, our automated ETL parser successfully matched interface data against engineering specifications with 98.6% accuracy. In the domain expert review, industry signaling specialists validated our symbol layouts and object models against strict signaling principles. For the factory acceptance test, we conducted 5 rigorous testing rounds covering normal operations, deliberate fault injections, and emergency stopping scenarios. A total of 62 change requests were recorded, addressed, and successfully closed. Finally, in the user acceptance test, principal signaling testers and operators validated the end-to-end road setting workflows, confirming the platform's high usability and operational fidelity. Evaluating the system against its core technical metrics demonstrates satisfying performance. Extraction precision achieved 98.6% automated extraction accuracy, drastically cutting down data preparation time. Real-time responsiveness, the end-to-end data update latency remains strictly below 150 milliseconds, ensuring smooth real-time HMI feedback during dynamic train movements. Correspondence testing passed 100% of correspondence tests across the entire loop, from simulated TCS commands through interlocking logic processing to trackside status reflection. In addition, this platform directly promotes sustainability by eliminating the need for energy-heavy physical test benches, hardware requirements, and also can be used for other purposes such as simular and/or maintainer induction or training. In conclusion, we have developed, implemented, and validated an integrated simulation platform for Electrologix interlocking data testing that completely removes reliance on physical trackside hardware. For future scope, we plan to integrate an internal automated scripting engine for batch test case execution, Incorporate artificial intelligence for automated safety verification and anomaly detection. Expand the architecture to support multi-station mainline networks. Thank you very much for attention and your time.